Assalamu alaikum. I am Abdul Shakur. The topic of presentation is selection of suitable type and placement of fault current limiter in a power network with embedded distributed generation. We are supervised by Sir Shoaib Ahmed Sheikh and our co-supervisor is Sir Fawad. First of all, our presentation consists of introduction, problem statement, literature review, aims and objective of the project, methodology, results and discussion, then conclusion, and after that references with future recommendations. DGs are becoming more common supplement to the traditional central power generation. DGs have the advantages because they are close to the load, so the losses are minimized. Customers get benefits from the DGs when there are power outages. Utilities can benefit from DG by expanding its capacity without physically adding new central power plants. With these advantages come some challenges since the DGs can be installed anywhere on the utility grid. Most utilities notice the importance of assuring a safe and reliable DG interconnection without having negative impacts on utility grid, especially the distribution power system. So the problem is when electric power system becomes more complex, the fault current level increases beyond the limits, leaving the system component such as circuit breaker or relays in overduty condition or in faulty condition. High penetration of DGs cause several technical issues in which the most important is high level of fault current. Power systems are becoming more complex with advances in distributed generation. It is great challenge to secure the stability of such system from high level of fault current. Protection of system is highly dependent upon the limiting the fault currents. How to limit those fault currents? By the help of using FCL, fault current limiters. So to find the optimal placement, we have gone through these literature reviews. First of all, the title of the first paper was a review of renewable energy resources, sustainability issues and climate change. This was about the type of DGs and their energy access, energy security, social and economic development. Then second most important literature paper we have gone through was about the fault current limiters, their development and technical aspect. This was about different type of FCLs that we have studied. Then after that we were searching for optimal allocation of fault current limiters in power system. Then we have gone through the paper which have used novel approach to determine the optimal number and location of FCL, which was genetic algorithm. After that we have gone through the optimization technique, which is particle swarm optimization, development and application resources. This paper focuses on the engineering and computer science aspect of development and application and resources related to particle swarm optimization. After that, aims and objective of the FIP is to ensure the safe and proper usage of DGs in existing system with the help of fault current limiter. Then second one is selecting the optimal placement of fault current limiter in standard IEEE bus systems with DGs. Methodology. The methodology we have used for implementing this project is simulation of standard IEEE bus system, implementation of DGs at different position, implementation of fault current limiters in that IEEE bus system with DGs, then implementation of particle swarm optimization for searching the optimal place for the fault current limiter. The software we have used is PSSC and MATLAB for PSO. Here is the PSO algorithm. First of all, going through its mathematical model, its first equation is about velocity update equation, which has three components. First one is inertia of that particle of swarm. Second one is its personal component, which or also we can call it cognitive component. The personal component consists of its personal position minus its original position. Then social component is the global component, which is its global position, best position minus its original position. This search for its global optimization and this search for its personal optimization. There are two constants used in this. First of all, when we are in start and searching for optimal position, we increase the global coefficient. Then after that, when we get the direction of that optimal place, we increase the personal component. After that, when we get the velocity of that component for next iteration, we update its position in next iteration by its original position plus its velocity. This was the mathematical model. Then, going to its algorithm, first of all, we initialize our swarm. In our case, it was the initially placement of the fault current limiters in system at any line. Then after that, we evaluate the fitness function or objective function. In our case, it was the violation of breaker. We have to minimize that violations. Then we have updated the velocity of each particle if there is updation needed for its another position. Then updated the position of that particle. If that updated position is the optimal position, then this system stops. Otherwise, the iteration continues.
We start our analysis with IEEE 6 bus system. This is the single line diagram of IEEE 6 bus system when there is no DG or no fault current limiter added into the system. Here we can see we have added a single DG on bus 6. This is the comparison of voltage and current profile of IEEE 6 bus system when there is a single DG and when there is a single DG on bus 6. The left side graph shows the voltage profile of IEEE 6 bus system when a DG is added, and the right side graph shows the current rating when a DG is added into the bus 6. We can clearly see that current is increased when a DG is added, thus violating the current rating of circuit breakers. This table shows the reactor placements in IEEE 6 bus system. We have generated various swarms to see their placements and to find the optimal placement. Next, we have when a single reactor is added on the line and when a single reactor added on the terminal. We can clearly see when a reactor is added on the line, a number of circuit breaker violation is reduced, while when we have added a reactor on the terminal, almost all the number of circuit breaker violations has been reduced and has been up to nominal system.
This is the 14 bus system. It's SLD, single line diagram of that system in which we have implemented FCLs and DGs. First of all, we have placed the DG at bus 10, which was optimal position for DG. We have gone through literature review for this. This is the voltage profile of that bus when the DG is added. This is and those all buses when the DG is at 10, and this is the current rating of all the circuit breaker in those lines when DG was added. These are those fault current limiters we have placed in line 15 to line 5 at different position after the iterations. This is the 7 line position of the FCL is the optimal location for that DG, which is the violation in which the violation of breaker is 8. These are the results comparison when we have placed DG at the any other random placement of the line, and this is the optimal placement at line 7. When DGs are increased, for example when there are two DGs in the system at bus 10 and bus 14, then this is the voltage profile of all the buses, and these are the current circuit breaker ratings when the DGs were added. These are all the fault current limiters ratings, and the 15 number line is the optimal location, as we see that there are 8 violations in the system. These are the graph exactly showing the difference between random placement and optimal placement of the reactor in the system when there were 2 DGs.
Next we have IEEE 30 bus system, and this is the single line diagram of IEEE 30 bus system. We have added single DG on bus 30. We can see the voltage profile and current rating profile of IEEE 30 bus system when a single DG is added on bus 30. When we have added a DG on bus 30, the current is increased beyond the limits and thus violating the current rating of other protective devices such as circuit breakers. We have placed now a single reactor to see its effect. This is the comparison of random placement and the optimal placement when a single reactor is added into the system. Um, by adding a single reactor, the number of circuit breaker violation is reduced. Next, we have added the same single digit, but now we have added double reactor so that we can minimize the number of circuit breaker violation. Then we have added two digits into the system, a digi at bus 29 and the second digi on bus 30. Again, by adding two digits, the current and the voltages have been increased, violating the current rating of circuit breakers. Now we have added a single reactor when we have added two digits into the system. This is the comparison of random and optimal placements of the reactor. Next, we have double reactor comparison. This is again the comparison of random placement and the optimal placement of two reactors. Now we have finally added four reactors and have got significant results. When we have added four reactors into the system, the number of circuit breaker violation is reduced up to 54. The total number of circuit breakers is 82 into the system. There are total 41 branches of the system. This is, in the nutshell, this is the optimal placements of reactors in every case. In the single reactor case, we have 62 number of circuit breaker violations. Again, in the single digit double reactor case, we have 56 and so on. We have analyzed the system. We have analyzed the three systems: IEEE 6 bus system, IEEE 14 bus system, and IEEE 30 bus system. Our purpose of this project is to investigate the impact of fault current limiter on the fault current level, losses, and stability of power network with DG connection. We have used particle swarm optimization technique for the suitable placement and size of fault current limiter into the system. The proposed technique is tested on IEEE 14 bus system and IEEE 30 bus system using Power Systems Formulator for Engineering PSSE. These are the references we have used throughout our research. In the future, what we can do, we can try different type of fault current limiters. In our case, we have used inductive type fault current limiter. We can also use different algorithm to see and to find the optimal placement of fault current limiter reactors. Thank you.